Assalamualaikum and good day to the panel. My name is Umairah BINTI WAHAB. Will present effect of glazed roof tile with reflection on mechanical properties of eco-friendly concrete. Roof tile waste is supplied by Golden Clear Sdn Bhd. Why did the company participate in this project? This is due to the fact that company is surrounded by piles of roof tile waste. Piles occur when the roof tile has a defect or when the final product does not meet the requirement. Because of that problem, roof tile waste become prospect for replacing normal aggregate. Therefore, this study explored the possibility of roof tile waste to be used in mixture of concrete. In order for roof tile waste to replace aggregate in the mixture, it should contribute to the standard performance of the concrete. To replace the sand with other material as a fine aggregate, the characterization of raw materials such as sieve analysis need to be obtaining in the mixed ratio because wastes are not directly ready or prepared for replace the material for fine aggregate. To perform characterization analysis such as SRD, SRF, and SEM in order to ensure that the roof tile waste is suitable to replace aggregate. It is helpful to understand how the qualities and properties of recycled roof tile waste aggregate affect the concrete mixture. The objective of this project to characterize and analyze the physical properties of roof tile waste for replacing fine aggregate in green concrete, to analyze the mechanical properties of green concrete produced using recycled roof tile waste as a fine aggregate, and to characterize the microstructure of green concrete produced using roof tile waste. The methodology for this project contains of 4 phases, which is phase 1 preparation raw material, phase 2 raw material characterization, phase 3 mixing process, and phase 4 concrete analysis. 2 cycles of grinding are required to generate fine aggregate in small size. The first cycle was done with the Rossel cutting crusher machine, which was used twice to grind the 5 mm size. The second cycle grinded used planetary ball milling to reduce the size from 5 mm to 0.15 mm in 20 minutes using 4 large and 6 small balls. Sieving process start with wash the sample, which is only for sand, and dry in the oven. The initial weight of sand, GRTW, and all the sieve was recorded. Using a sieve machine, sample was poured into the sieve and vibrate for 10 minutes. Lastly, the final weight of sample retained at every sieve was recorded. Make design process was calculated using Bergling Research established BRE method. Grade design M24 type of cement OPC fine and coarse aggregate is the important data must be collected. Water cement ratio and water content was the reference for the compressive strength and workability of the concrete mixture. All the tests based on British standard in different pipe. Concrete tube in cast on site using M25 concrete grade, which a mixing ratio get from BRE method, which is 1 to 2.5 to 1.38 to 0.45 for cement, fine aggregate, coarse aggregate, and water. Slump tests were determined according to British standard shown in the table and focus on slump fall value 60 to 180. The volume of slump cone was calculated and the value is 0.0055 cubic metric. The volume used for each mixture of cement, fine aggregate, coarse aggregate, and water of the total quantity that used. The slump test begin with the inner surface of the slump cone being sprayed with lubricant and the 50% of GRTW mixture being placed in the slump cone. The concrete mixture was timed 25 times by used steel rod for every 1/3 height, and the slump fall was recorded. The step for 10% and 20% same as 50%. For control sample, the slump fall is 80 mm. For 10% and 20%, the slump fall value is 100 and 110 mm. For 50%, for slump fall is 30 mm. According to BT standard, 50% of GRTW was out of the range because the range between 60 to 180 mm. Mixture of the concrete was compacted into cube mold which dimension 100 x 100 x 100 mm, and the mixture was dry into the mold. The initial weight of control concrete was recorded. The control cube was immersed into the water that called curing process was being tested according to their age, which is 7, 40 and 28 days. The preparation of 10%, 20% and 50% of GRTW same as control sample preparation but different in the mixture of the concrete. 9 cubes were made of each sample. The sample size of sand employed in the CV method is 0.705 gram and the final weight is 0.704 gram. The sample size of GRTW employed in this sieving method is 0.504 gram and final weight is 0.502 gram. In this case, the difference between initial weight of the sample sand and GRTW is not more than 0.2%. When the mass before and after sieving differ by more than 0.2%, do not use the result for accepted purpose. The highest amount of sand and GRTW sample aggregate retained is at sieve size of 1.18 mm and 0.30 mm, which is 33% of the total weight. Generally, both sample can be considered as the well-graded fine aggregate in that it can reduce the void content. For the SEM analysis image, the GRTW sample shows some pores that existed compared to the sand sample. Surface area for sand less than compared to GRTW. Because of its high porosity, the calcium silicate hydrate responsible for the hardening reaction has a huge specific surface area when hydrate cement hardened. Single point desorption total pore volume less than of the pore for sand than GRTW. Due to the bigger pore volume, the higher surface area, which is large pore size, has higher absorption capabilities as the concentrate is increased, even though the GRTW shows some pores, but in terms of the pore size is less than sand. Eco-friendly concrete water absorption and density. The water absorption for 10%, 20% and 50% of GRTW decrease. Water absorption should not exceed 3% or 2% under critical condition according to marinate regulation. Some research found higher water absorption in concrete for 20 until 40% ceramic aggregate substitution as compared to the control concrete. The increasing water absorption of ceramic aggregate concrete at higher replacement to the porous concrete structure result from the lack of cohesion among tile aggregate. A decrease occurs due to strong bond mix of fine aggregate in concrete, which is sand and GRTW. The density of the control mix concrete almost same as the standard. It can see that even though the slump value chosen the 20% for pass to use, but the density value show the highest amount added. The density achieved will be determined of the aggregate type chosen. Eco-friendly concrete composite strength. The discussion of the result begin with the lowest performance by 20% of GRTW and the highest performance by 50% of GRTW. The finding highlight that 50% GRTW show an amazing improvement of 13% as compared with the lowest performance. Even though the result for the slump test of 50% of GRTW is out of the range. On the other hand, our finding revealed that the performance of 20% replacement of GRTW dropped by 5.8% respecting the control sample. The cause could be that the flat surface of the aggregate prevent the aggregate from engaging with the concrete. Eco-friendly concrete crystalline paste. SRD analysis is the method to find mineral composition like calcium silicate hydrate, calcium aluminosilicate hydrate, portlandite, yttriite present in concrete. The higher peak for control sample same as 20% and 50%, which is contain calcium silicate hydrate and calcium aluminosilicate hydrate, but different for 10% of GRTW, only calcium silicate hydrate. The peak rate by the diffraction of portlandite show the same intensity in all type of concrete. As the cement content was lower, this support that the particle effect mixed by ceramic will accelerate cement hydration. Eco-friendly concrete Surface morphology. A CM image of the concrete with different weight fraction of GRTW obtained with the magnification of 5,000. The concrete content of 20% GRTW has a less pore compared to 0%. The microstructure of 0% GRTW concrete show that the pores of larger width are present in the concrete while the concrete is not densely packed. Those results prove that the using of recycled ceramic aggregate can molarize distinctly the structure of the concrete. Based on the comparison of the microstructure of concrete mix, it is clear that hydration process in the mix with supplementary material was different from the conventional concrete mix. In mix of 20% GRTW, the hydration process was quite similar to the normal concrete mix, but development of calcium silicate hydrate gel in the mix was quite lesser compared to the normal concrete. In conclusion, the grinding process of GRTW as a fine aggregate is done in accordance with BINTI standard. In terms of slump testing, 20% GRTW yield the best workability result when compared to other percentage GRTW and control sample. The water absorption of concrete containing 0%, 10%, 20% and 50% GRTW does not exceed 3% or 2% under critical condition according to the marinade regulation BINTI standard. When compared to the control sample and control with varying proportion, the 50% of GRTW has the maximum compressive strength. With a 10% weight fraction of GRTW, the data pattern start to decrease, then start to increase with a 20% and 50% weight fraction of GRTW. Calcium silicate hydrate, calcium aluminosilicate hydrate, portlandite and yttrium are mineral composition found in concrete mixture. Surface morphology for 20% of GRTW show the less pore among the other weight fraction.